Okay, so I have your exams that I'll hand back after class. If you have any questions about the exams, email me or come see me. I did put the answer key online, so you can take a look at it. I will be putting midterm grades up for everyone by the end of the day or so. So we have those. And I put the next two classes materials up on videos, and we'll as we get to problems here at the end of the week. So at least for the next 15 minutes, I have no intention about talking about the virus that should not be named, that is just creating all sorts of issues. Okay, so where were we at? Here's where we were at when we last were here. We were adding groups to the benzene ring. And the idea was that if we added an electrophile to the benzene ring, if it's a strong enough electrophile, it will add to the double bond, to one of the double bonds of the ring. We make a carbocation that then we could write resonance structures for, which I'm not going to at the moment. But then if a nucleophile adds to that carbocation, it destroys the aromaticity of the ring. So instead what's going to happen is we're going to lose an H plus off of the carbon where the electrophile added. So I'm going to lose my H plus, and I'm going to reform the very stable aromatic ring. So in the end, what I've done is I've replaced a hydrogen with the electrophile. And so this is electrophilic aromatic substitution. So now what we have to do is we have to talk about, well, what reagents will generate our E pluses that are going to substitute in the ring. And so just to kind of review and get ourselves back into the mode here, if we take our benzene ring and we add to it HNO3 and H2SO4, that set of reagents is going to generate an NO2 plus, which then is going to substitute for a hydrogen, and I'm going to make nitrobenzene. So that was the first set of reagents. And if you don't have 3x5 cards on these, then as we go through these reagents, or whatever method you're going to use, you're going to want that, because on Wednesday's quiz, part of that quiz will be, I'm going to ask you to put down the reagents that you are that you would need to use for adding each group, because you'll have to know that. So that was number one. Number two was, if we wanted to add a halogen, we could use either Br2 or Cl2. Our catalyst would be either FeCl3 or FeBr3, or it could also be aluminum trichloride or aluminum tribromide, depending on what halogen I'm using. Tribromide. And that would allow us then to put a halogen on the ring. So we could use either a chloride or a bromide to do that reaction. Okay, just the chlorine or bromine itself will not react with the ring. It needs the iron or the aluminum. See, coughing would not normally even raise an ire in a round, but now we're, again, unnamed. Third one we talked about, SO3, H2SO4. When we mix SO3 with H2SO4, I'm going to protonate the SO3. So that's going to generate HSO3 plus, and that's going to generate then a sulfonic acid, the SO3H. That group, when we talked about this last, if we replace the OH with Cl by using like ECl3 or SOCl2, that was making the tosyl chloride. So we've kind of seen that one before. And so those were the three that we talked about that were just kind of reagents. The next one was I want to add an alkyl group. If I want to add an alkyl group, I need to make the carbocation. How do we generate carbocations? Traditionally, what we've done in the past is we've taken an alcohol and added H plus to it. So the H plus protonates the OH, the water leaves, that gives us a carbocation that'll add to the benzene ring, or we could think about reacting H plus with a double bond, add the H plus Markovnikovly, make the carbocation, which would then add to the ring. So those were methods we used to make the carbocation. And then we learned that if I want to add by what's called Friedel-Crafts alkylation, I'm going to take my alkyl halide and I'm going to react it with aluminum trichloride so that the chloride is removed by the aluminum to form the carbocation and then form AlCl4 minus. So that's the Friedel-Crafts method of making a carbocation, and any carbocation will add to the ring. And that's kind of where we're going to pick up today. Okay. So that's what I want to start with, is making these carbocations in terms of limitations. So one of the limitations of this Friedel-Crafts alkylation is that you cannot add a straight chained alkyl group to the benzene ring. So if I wanted to take my benzene ring and I wanted to add, let's say, a CH2, CH2, CH3, a propyl group, if I want to add the propyl group to the ring, I cannot do that using Friedel-Crafts alkylation. You might say, well, why don't we just take aluminum trichloride and react that with propyl chloride? First of all, you may be saying, but wait, any primary halide, how are you going to form a carbocation out of that? And that includes taking something like aluminum trichloride and reacting it with methyl chloride or even ethyl chloride. Can you do that reaction? Can you add a methyl or ethyl group to the benzene ring using Friedel-Crafts? And the answer is yes, you can do that. But what happens is you don't ever form a methyl or an ethyl carbocation. What happens in this case is, because those two molecules, methyl and ethyl, cannot rearrange. So what's going to happen is your aluminum trichloride is going to pull the chlorine off. It's going to pull the chlorine off until you get enough delta positive charge on that carbon that it's then going to add into the ring. So you never truly form a primary carbocation. You only form enough delta positive charge as the aluminum is pulling the chlorine off to get to a delta positive term that will then add it to the ring. So we can add methyl chloride or ethyl chloride and make methyl-ethyl benzene, but we're never going to form a true carbocation. Why do I say that? Because what's going to happen with the propyl group is the aluminum is going to take the chlorine away, but in this case, this hydrogen can shift. And so as the aluminum starts to pull the chlorine away, at some point the hydrogen is going to come over, is going to do a shift, so that what I'm going to end up forming is, I'm going to end up forming an isopropyl carbocation. So with Friedel-Crafts alkylation, you can end up with hydride and methyl shifts. Just like we had before. Now, when we had these before, what I said was, I need to tell you when to shift. Except one time. And the one time that I will not tell you when to shift is with a primary halide. So when you're using a primary halide in Friedel-Crafts, you're going to get a shift to the secondary carbocation. So if I tried to do this, if I tried to take my benzene and add propyl chloride to it in order to make that molecule, in order to make propylbenzene, that will not work. What will you get instead? You will get isopropyl chloride. So with aluminum trichloride, you're going to get isopropyl benzene because of the shift. And that is the one time that I will not tell you to shift. You're going to have to know that. All the other times I'll probably, I'll tell you, or it'll be apparent when to do the shift. But in this case, if you try and react anything other than methyl or ethyl, any straight chained alkyl halide in Friedel-Crafts, you're going to get a secondary carbocation. You're going to get just one hydride shift. So that means we can't make straight chained alkyl benzenes by Friedel-Crafts. There's going to be another way to do it, which we're going to go into now. But that's the one time I will not tell you when to shift. I'll expect you to know that. Starting Wednesday on my quiz. All right, everybody kind of with me? Still? It's not 8 o'clock in the morning and everybody's still. I want my break this week. The power was out in this building from Tuesday to Saturday. Don't eat anything perishable from that little room over there. If there's anything left, it's gone. So how do I add a straight chained alkyl benzene? Here's how I'm going to do it. I'm going to use Friedel-Crafts acylation. So what I'm going to do is Friedel-Crafts alkylation is when you add an alkyl group. Friedel-Crafts acylation is do the same thing, only in this case, let's use what's called carboxylic acid chloride. So I take a carboxylic acid and I replace the OH with a chloride. If I react the acid chloride with aluminum trichloride, the same thing happens. The aluminum is going to take the chlorine away, Cl-, and I'm going to end up with a carbocation. And that's called an aselenium ion. Now, if in mass spec you talked about the stability of aselenium ions, this turns out to be stable because I can take one of these lone pairs and I can move it down to form a triple bond. The oxygen will now have the positive charge. But an aselenium ion turns out to be stable because it does have that resonance structure. So in mass spectrometry, at least in my lab section, we talked about cleaving the carbonyl bond to form that carbocation because it was very stable, because of the resonance structure. So that is So that's what we're going to form. We're only going to add the C plus to the ring. So when we add the C plus to the ring, then we're going to end up with what's called a phenyl ketone. That's a phenyl ketone. When a benzene ring acts as a substituent, it changes name. It's called phenyl because benzyl is a ring with a CH2 on it. A ring itself is called phenyl. So that's a phenyl ketone. Notice that what I did was I added a 3-carbon chunk, a 3-carbon piece to the benzene ring. So now what I need is I need to get rid of the carbonyl and turn it into a CH2. Now that's a reduction because I'm going to replace the oxygen with 2 hydrogens. How am I going to do that? Well, I think when we talked about phenyl ketones before, I said, oh, what reagent would you use to reduce the ketone to an alcohol? And then after some minutes and page turning and everything else, we said if you want to go from ketone to alcohol, you use lithium aluminum hydride or sodium borohydride. But there's 2 other reagents that I can use that will not stop at OH. It will take this all the way down to CH2. So if I want to convert that phenyl ketone into a CH2 group, which will then allow me to synthesize straight-chained benzene rings, I need one of these 2 reagents. And they're kind of interchangeable, although they probably aren't. There's probably restrictions on them, but we're going to use them interchangeably. The first is to use N2H4, KOH, and heat. Remember, that's what the triangle means. So N2H4 is hydrazine, KOH, and heat will reduce the carbonyl all the way down to a CH2. And we can also use zinc mixed with mercury, a zinc-mercury amalgam, HCl, and heat. Those are 2 different sets of conditions, but they both will do the same thing, which is reduce the carbonyl down to the CH2. The top one is called Wolff-Kishner. There's a C in there somewhere. Not there. Wolff-Kishner reduction, and then the bottom one's called Clemenson. The names are not sufficient to get you full credit. So you have to know the names. But that's what they're called, both Wolff-Kishner and Clemenson reductions. So the idea here is the purpose of Wolff-Kishner-Clemenson is to reduce phenyl ketones. The usefulness in that is that the phenyl ketones then are a way to put a straight-chained carbon group on the ring and then reduce it down to the straight-chained alkyl group. Because straight-chained alkyl halides undergo rearrangement, you can't put those on the ring, so you've got to do 2 steps. Phenyl ketone, then Wolff-Kishner or Clemenson reduction. All right, so that's the Friedel-Crafts acylation. Any acid chloride that you can make, you can add to the ring by using aluminum trichloride. Now, I would be remiss if I did not say, okay, where does the acid chloride come from? And I would say the acid chloride comes from the carboxylic acid. And what reagent would I use to convert the carboxylic acid to the acid chloride? That is, so let's write down HCl. and cross it out. This is the one case where HCl doesn't work. That's okay. It was going to get mentioned then anyway. So this is the one case where HCl won't work. So we need the alternative reagents, which are SOCl2 and PCl3, PCl5. So those are the reagents that we would use. We would use SOCl2 or something like PCl3. You could also make the acid bromide as well, but typically we make the acid chloride. HCl is the one reagent that will not work. So that's the one we don't want to use. Okay. But convert your carboxylic acid to an acid chloride, and then you can go ahead and add it to any ring, and you can reduce the carbonyl group down to the CH2 by Wolff-Kirchner or Clemmensen.
You talked about how to pretest alcohol so that you don't accidentally get it wrong. Is there any way to protect the wrong as the reaction if you wanted to use it?
Yes, and that is Friday, if we get there. If we don't get there on Friday, it'll be next Monday. So yes, that's our first. Well, that's going to be our second protection. Yes, is how to protect carbonyls. Yes, there will be a way to do that. We have a lot of aromatic reactions in between now and then. All right, so is everybody kind of with me? So we have now what? We've got the three reagents. We've got Friedel-Crafts alkylation. We've got Friedel-Crafts acylation, and now we have Wolff-Kirchner Clemmensen to reduce those down. So there is six or seven reactions right off the bat. So we can add groups inside the benzene ring. Substitute a hydrogen with that electrophile. But now the question becomes, great, so I know all these reagents. 7 of them. Right, it'll probably be double that amount when we're all said and done. A little more than double that. But benzene's boring. Right, because I got 6 hydrogens, it doesn't matter which one I replace. Let's make life a little bit more interesting and realistic. Let's put a group on the ring, and now we have to ask the question, all right, which hydrogen is going to be replaced by the electrophile? Is it going to be the ortho, the meta-hydrogen, or the para-hydrogen? And if you're hoping that it's just random so that we can move on, then nothing is just random. Right? There's a system here. And so where that group, where that electrophile will go relative to the group on the ring, will it go ortho, will it go meta, will it go para, is due to what type of group we have on the ring. So now what we have to do is now we have to go back and we have to create our electron donating, electron withdrawing group list. And this list comes because basically I'm going to react that electrophile, that ring, which is a nucleophile, with the electrophile. So what we do is, if we replace different groups on the benzene ring, we measure how fast the reaction is. The benzene ring itself is a nucleophile. That means you want it to react faster, push electron density into the ring, make it more electron rich. You want to make it react slower, take electron density out of the ring. Electron donating, electron withdrawing. We're going to change the terms a little bit. So now we go back and we write our list from number 1, and I'm going to add a 10th group down to number 10. So number 1 is a nitrogen group. It turns out that nitrogen groups make the ring react the fastest. Why? Because nitrogen groups donate the most electron density to the ring. Followed by oxygen, followed by a benzene ring, followed by an R group. Those were all of our electron donating groups. Now I'm putting them in order. Most to least. Then we have hydrogen, because hydrogen is the baseline. So all four of those groups make the benzene ring react faster than just benzene itself. Okay, so this is number 1, this is number 2, 3, 4, and number 5 is hydrogen. Those all react faster than benzene. And we could go back and review even more, because the first 4 groups, or the first 3 groups, donate electron density by resonance. And what donates by induction? The alkyl group, that's why it's last. Okay, now once we get past hydrogen, we have our electron withdrawing groups. If you pull electron density out of the benzene ring, it's going to be less nucleophilic, it's going to react slower. So what's the order there? The order there is number 6, halogens. Why halogens? Because they withdraw electron density by induction. Number 7 would be a carbonyl. So now I'm getting into withdrawing electron density by resonance. Number 8 is going to be a C triple bond N. Number 9 is an NO2 group. And I'm going to add 10. And 10 is going to be a nitrogen with 3 alkyl groups attached to it, which then gives the nitrogen a positive charge. So halogen withdrawing by induction, that's weak. Then carbonyl, C triple bond N, nitro, and then what's called ammonia. Those decrease the rate of reaction of the benzene. So also on Wednesday, in our quiz, I will ask you to fill in a table with those groups from number 1 to number 10. Actually, from number 1 to number 10, I'll give you number 5, the hydrogen. We have to know that, and it'll be, by the end here, it'll be clear why we have to know that. Right? Hopefully you haven't lost what's electron donating and what's withdrawing from the last couple weeks. But if you did, get it back in there, because we're going to need to know that as well. So these groups that are electron, these were the electron donating groups. They're going to be called activating. I'm going to call those activating groups, because activating is going to mean that the benzene ring reacts faster by putting those groups on it. The groups that are electron withdrawing, number 6 through number 10, those are all going to be electron withdrawing groups, and those are going to be what we call deactivating groups. I know before the exam somebody said, what's activating and deactivating? That's the terminology we use for electron donating and withdrawing groups, now that we're talking about the group's effect on a benzene ring. So they all react slower than benzene. So when you put a group on the ring, it affects the rate of the reaction of that ring. But that's not where I started, right? I started with the issue of where's the group going to go, ortho, meta, or para? Well, it turns out that all of the activating groups, that electrophile is going to add ortho and para to the group that's on the ring. The group that's on the ring is going to be called a director. And all of the activated groups tell the electrophile to go to the ortho position to form one product go to the para position to form the second product. So we're going to get a mixture of ortho and para products. When there's an activating group on the ring, it directs ortho and para. It directs E+. All of the deactivating group was with the exception of one. So halogens and all of, or sorry, not halogens, the carbonyl and all of those are going to be then the meta-directors. So when we do a reaction with a carbonyl on down, we do not get much ortho and para product. We get mostly, if not all, meta product.
Is ortho and para going to be
We are going to treat it as if it's both products, but then later on we're going to decide one over the other. So we'll do a problem and I'll get a little bit more into that, but right now you're going to write the ortho product and you're going to write the para product. And then if it's a deactivated group with the exception of one, it's going to be deactivating. What's the exception? The exception is halogens. Halogens are deactivating, but they are orthopara. That's the exception. So, how many times have we had this in the past? Right, organic chemistry is all about this yin and yang. Right, you use one set of reagents, you get Markovnikov and anti-Markovnikov. Zaitsev, not Zaitsev, or Hoffman. So you get orthopara or meta. So that you're going to have to remember as well. Because if I make the table up, the table is going to be pretty empty. So you're going to have to put the group. Is it activating, deactivating? Is it orthopara or meta-director? So that table is going to be important, and there's a couple of versions of that table in the PowerPoint notes that are in today's folder. So our ultimate goal here is, let's add an electrophile to a substituted ring. What would be the major product of that reaction? So let's start with toluene. Toluene is methylbenzene. I'm going to go ahead and I'm going to add nitric acid and sulfuric acid to the toluene ring, to the ring of toluene, of methylbenzene. When I'm doing this kind of problem, the first thing I need to know is what reagent or what electrophile does HNO3 and H2SO4 produce? Should be a minimal amount of page turning here. NO2 plus. So I'm going to add an NO2 plus to the ring. I'm going to substitute for a hydrogen. So that's the first thing I need to know is what is my electrophile? NO2 plus. The next question is, where is it going to go? Methyl, the group on the ring, is directed. It tells with the NO2 where to go. And so, what is methyl? Electron donating, electron withdrawing, orthopara, or meth? It's orthopara director, it's activating. So the methyl group says to the nitro group, you're going to the ortho position, you are going to the para position, and so I would get a mixture of orthonitrotoluene, and I would get para nitrotoluene. And the way I'm going to ask you to write the products is, when it's an ortho-para director, you're going to write both the ortho and para products. If it's a meta-director, you're just going to get one. You're going to get meta. Now, to your question of, is there more ortho or more para? I don't care. Because these are the major products of the reaction. You might say, but what about sterics? Right now, we're not going to invoke sterics. But you could think about invoking sterics. You could say, what if the group on the ring is really big? Can that group fit ortho? Maybe not as well as it would fit para. What if I get adding a big group to the ring? Probably going to get more para products. So give us a day or so, and we'll begin to invoke sterics. But right now, and on the next exam, I'm going to want you to write both ortho and para if it's an ortho para direct. And then later on, I'm going to say, I'm invoking sterics, I'm only going to get the para product. But not today. So then I get those two products, ortho nitro and para nitro. Now, when people start out here, when they start looking at this reaction, this is the way that you do not want to think. So if you're a person who says, I don't want to hear that because I don't want to know what you don't do, put your fingers in your ears and go listen to this. But a point of confusion that sometimes people have, they'll say nitro. It's a meta-directory. Yeah, not when it's an electrifier. The group on the ring is directed. So I don't care what the electrophile is. It does not self-direct. The group on the ring tells the electrophile where to go. So don't get confused like that. And if you're like, you should have told me to not get confused like that. The group on the ring is going to be the direction. Everybody come with me? Okay. What happens if there's more than one group on the ring? So number one, in order to answer that question, you need to know your chart. At least from the standpoint of what's orthopara and what's meta-direction. Now you might say, do we really need to know it in order? Yes. Because I think Top Hat still uses the approach that I used circa 2000-ish. And that is that when you have more than one group on the ring, you could say, oh, so let's take the group on the left here. Let's take the ortho nitro and let's say, you know what? Let's add another NO2 plus to this ring, to that ring, to the ortho nitro toluene. Where's the nitro group going to go? And you can take the approach and say, well, where's the methyl group? The methyl group is directing ortho and para to itself. Where's the nitro group directing? Well, the nitro group is directing meta to itself now that it's on the ring. And you can say, well, if they both direct to the same position, everybody's happy. That's where you put the nitro group. If they direct in opposite positions, then what do you do? And you take the group that's higher on the chart. And I used to teach it that way until like about 2000. And it was in the other building, which might have been the day I broke my right arm and didn't know that it was broken, so I tried to this. It was not for that. That was a fun day. But anyway, a student was like, do we really have to do that? Do we really have to look where the groups are pointing, where all the groups are pointing? And I'm like, well, what's your alternative? And the alternative was like, well, worst case scenario is that the group that's highest up on the list is going to be the one directing, so why don't we just worry about that one? I'm like, that's genius. I think I'm going to use that for the next 20 years. And so we don't have to look at each group. All we got to do is say, who's higher on the list, methyl or nitro? Methyl's number greater than 8 or something like that. So I mean, if you have two activating group, which one's more activating? If you got an activating and deactivating, activating wins. Two deactivating, which one I guess is less deactivating, but which one is higher up on the chart? So you have to know the positions of the groups on the chart. Yes, you do. Why? Because of this situation. So I just say, you know what? Methyl group's higher on the chart. It's directing. It's directing the next nitro group to go ortho and para to itself. So now I'm going to get two more products. I'm going to have the first product where the nitro group is going to add ortho position, and then I'm going to take, and it's also going to direct the nitro group to the para position. So those would be the two products that you get from that reaction. So whenever you have multiple groups on the ring, whoever is the highest on the chart does the direction. What if you have the same group in different positions? Well, now if they're directing to the same positions, that's where the group's going to go. If they're directing to opposite positions, it's going to go everywhere. So you're going to end up with a lot of multiple products. So in this case, I would get those two nitro polymers. And then let's just take the molecule on the left. Let's do that one more time. So add one more NO2 group, and if I, what would be called exhaustively nitrated toluene, all of the products are going to be the trinitro toluenes listed there. Because the methyl group is going to direct all the nitro groups eventually to 1, 3, and 5. Or, I'm sorry, 2, 4, and 6 relative to it. So that's going to be the final product regardless of what. So the idea here is that the highest group on the chart is going to do the direction. And if two groups have the same priority and they point to different directions, then you're just going to sequentially add the group to those two different positions. So what role does the group on the ring have? Number one, it has a kinetic effect. Does it increase the rate of reaction? Does it decrease the rate of reaction? That's activating or deactivating. What about its direction? All the activating plus halogens do ortho-para direction. All the deactivating groups, with the exception of halogens, do methyl direction. Now, just something about this synthesis. So this is the synthesis of, and I think I did this before, of trinitrotoluene. That's right. And so trinitrotoluene along with nitroglycerin are, the family of its pre-1900s explosives. That really revolutionized a lot of things, right? Dynamite sticks allowed us to blow up mountains and get the railroads in California. So, Nobel was more triglyceride, or was nitroglycerin that you had to mix with clay in order to make dynamite stick. I don't know if you use in those little cartoon bombs. I'm not quite sure what TNT that is. But if you're going to make said explosives, particularly in this case, you've got a fine line to walk here. The first nitration, the benzene ring causes the first nitration to be pretty smooth because it's an activated ring. Once you put a nitro group on, there's less electron density. You're going to have to heat a little bit to get the second nitro group on. Once you got two nitro groups on, there's a fine line between heating it enough to get the third nitro group on and then heating it enough to explode and blow yourself up. So, it was a pretty dangerous business to be making explosives back in the PMP and nitroglycerin age, which is part of the reason why Nobel, had a number of family members below that, but so he ultimately turned his wealth into peace prizes and medicine and all of that stuff.
How do you put a nitroglycerin nowadays?
I have no idea. First of all, it's not pure. The little pill is not pure. Right? So, I'm not sure. Probably the same way they just make it in a metal container. This is the only one that I really talk about. This is the one where it would be like making maple syrup. where you have to sit on a three-legged stool. And it's not a three-legged stool in a triangle, it's a three-legged stool in a square, but one of the legs is missing, so that way you stay awake, so you don't either burn down the sugar shack thing, or you blow up the plant, because if you fall asleep, then it wakes you up when you hit the floor. So, activating and deactivating in this case take on a little bit of a role. All right, so these groups that are already on the ring direct. They're going to direct to a particular position. I just want to go back for one thing with our table. So on Wednesday's quiz could be kind of substantial because there's a number of things. First of all, knowing the reagents that we've talked about, as well as then also filling out this chart, but we might as well get it over with. Because you're going to need to know that and not forget it. What about the NR3+? So you could look at that and say, but that's just an induction. Does that make any sense? That an inductive effect would put that at number 10? And the answer is probably no. That induction isn't the reason for that. The real reason why, if you put an if you put an NR3+ group on a benzene ring, that it's going to react the slowest, is simply because if I put this group on this benzene ring, I've now made a positive charge on the ring that's trying to react with the positive charge of the electrophile, and that's not going to work out very well, because the positive charge of the ring is going to be repelled by the positive charge of the electrophile. So it's not that number 10 is because of an inductive effect, it's just because I'm putting a positive charge on that ring and trying to add something positively charged to it. So that's not going to work out all that well. So it's not an anomaly, it's just that's number 10. And to be honest with you, should it be there? Because we usually don't do those reactions, because they don't work in general. Even the nitrated groups are sometimes hard to get to react with. But as long as you're not like trinitrating anything, you could give a little bit and not have to worry about it. So the reasoning for why ortho-para-directors, why meta-directors are the way they are, and also why halogens are in between, are in the video for today. And so what I'm going to, or in the textbook, what I'm going to encourage you is take a look at that, and then I'll clean that up on Wednesday if you have any questions about that. But we need to know that table in order to do reactions, because once I put one group on the ring, I'm going to want to put the next group on the ring. Ultimately, by Friday, our goal here is to give you a benzene ring and say, make this compound out of it. So you got to figure out how to put that group on the ring. And then you got to figure out what order to put the groups on the ring, because if you put them in the wrong order, the groups go in the wrong places. So, on the next test, if you really want to look, the third test, you're going to see that I'm going to ask you problems where you take benzene and put the groups on them, but we're a ways away from that. On Wednesday, the idea is, these are actually Wednesday's probably, the video is online. Might get a little mess. No, it doesn't get messy yet. But we'll go over that as well. Wednesdays is how do we put different alkyl groups on the ring beyond Friedel cracks. And those reactions will save us a little bit of time of putting an alkyl group on the ring, free radically halogenating and doing U2 and all these other reactions. So if you take a look at that for Wednesday, then if you have specific questions, we'll kind of go over that and start to think about problems. Okay, so I'll email exactly what will be on the quiz. If you have questions about the exam, come and see me or email me.